Oh, I think it is now. Hello. This is my thesis made in collaboration with Haptic Architects with the supervision of Dr. Juan Vallejo. And yeah, so wood is one of the oldest materials humankind has ever used to build shelters. And after a hiatus in recent centuries, it is now enjoying a resurgence in popularity in the construction sector due to its promising potential to reduce the embodied carbon emissions of buildings. This is a synthetic version of my methodology, where basically I have a first part of literature review where I compare the embodied carbon factor of different products, and then the pros and cons of the light weight of wood. And then for my analytical work part, I analyze the case study building, where I then propose some alternative scenarios to it and analyze the results with life cycle assessments and dynamic thermal simulations. So what is mass timber? It's also called engineered wood product. It's basically layers of wood dried in a kiln and glued together. One of the most popular ones is glulam, where all the layers are in the same direction. Then there's also cross-laminated timber, more useful for surfaces, and LVL that is similar to glulam, but instead of having thick layers, you have like 3 millimeters small veneers. So as I said, CLT is typically the most carbon efficient mass timber, while LVL is the most carbon intensive. However, LVL and glulam can be compared qualitatively as both are ideal for structural elements, but LVL requires smaller sections, so you need less of it. Therefore, if we compare the embodied carbon of glulam and LVL products, the latter adjusted in size to be equivalent to glulam, we see that they are actually quite similar. Here the red values are for glulam and the blue for LVL. So literature shows how using mass timber structure instead of heavier materials such as concrete or bricks can bring materials and carbon savings, which is a good thing from an LCA perspective, due to also a reduction in the foundations and the thickness of other structural materials as well. But on the other hand, mass timber walls and slab translate to a much lower thermal mass capacity, making the building require more energy for heating and cooling than if it was made with heavier materials, and leading therefore more easily to overheating scenarios, which is quite a problem considering the climate heating situation we're in. But the embodied carbon savings are usually so high that on a whole life cycle perspective, it still makes sense to use mass timber. So this is my case study building. It's called W3. It was designed by Haptic, and it's currently nearing completion in the new King's Cross Central development. It's a 3-story community building designed to be very flexible. Currently, it's going to house a nursery, a coffee shop, and a gym. And inside here, we can see the glulam structure and the CLT slabs, and so also some steel structural elements due to some structural constraints. So my proposed scenarios were focused on the structure, the internal slabs, the external walls, and the core, because in the structural frame, my main objectives were to remove steel and consider LVL, since it has these interestingly lower sections. And for the internal slabs, basically in the project, there's many layers in the construction elements. So I was thinking if we can get a good performance with CLT and a higher density low carbon layer. In the external walls, instead of the current glulam columns and plasterboard, I imagine the possibility of having a CLT wall, and the core is now being built with reinforced concrete, so it can also be made with CLT, and that's another thing that I try to simulate. So the results show that in this case, the carbon savings can be obtained. Here, the glulam product chosen for this specific product was so carbon efficient that any LVL solution would have had actually higher embodied carbon. But in total, considering these scenarios, the final carbon emissions reductions brought by the combination of these design alternatives will be of around 63 tons of CO2. So in conclusion, careful design choices in mass timber construction can lead to significant carbon reductions. It is essential to analyze carbon emissions throughout the entire life cycle. And from my literature review studies and the analytical work, we understand that CLT is an optimal product for surface elements such as walls and ceilings, while glulam and LVL are ideal for structural elements. Although LVL allows for smaller cross-section, it is essential to compare actual products with LCA to quantify the mass timber product that will result in the lowest possible life cycle carbon emissions. Thank you.
Thank you very much. Good. Oh, thank you very much. Any question from the room? No? Well, I have one. In a climate where it's going to become quite wet and warmer, okay, what are the risks of using these kind of materials from a moisture point of view?
They're already doing it pretty much a lot all over the planet, and the way to build this is to basically take care of not exposing timber to the outside element, the outside air. And in the construction phase, as we can see here, the ideal thing is to protect the exposed parts where the veneers of the timbers are. And yeah, usually you do require some coating to protect especially the timber elements that are exposed to the outside weather. But it's all something that's been already studied a lot, and there are techniques to overcome this by indeed implementing especially coating. Sometimes some years ago, people were putting like cladding on top of the timber elements, but that's a bit of a carbon intensive process. So instead, for protection of this kind, usually it's done by applying some specific coatings that are included in the EPDs of the specific products.
Okay, and in your calculation, did you consider those coating?
I consider basically the entire things that were in the constructions part of this part. So yes.
Okay.
Yes.
Hi, thank you for the presentation. It's not a question, more as a suggestion maybe. So you're talking about timber. Can you put slide number 8, I think, please?
Sorry?
Slide number 8.
This one?
Yes. So you're adding all the layers that are down for your for your envelope. Did you consider, like, once you're doing the overall lifespan calculation for the energy, did you think of doing the study for the effect that timber could have on the internal thermal behavior? Like timber could be considered like as a material which is in between. It could be considered lightweight, or it could be considered heavyweight and thermal mass. So it could have an effect on improving the excess heat. Have you thought about that, or would you think of doing something, maybe push it more to study the thermal effect of the timber and thus reducing the cooling effect or whatever if needed?
It's something that I was interested in because the main issue of timber construction is indeed the lack basically of thermal mass is a big issue for operational energy and therefore operational carbon. In this case, I basically dimensioned the new CLT wall to get the same U value as the wall before. And to do this, I reduced the amount of the mineral wool insulation that is the purple layer there. But in my simulations, I didn't really found any difference in this case. Like even though I said the actual specifics of the CLT wall with its mass, I think these materials are just so lightweight compared to everything else that I also kind of expected a bit of thermal mass work in these scenario, but I didn't. The final operational energy numbers were very, very close to similar. So yeah, that's why I think it's important to couple timber elements, especially CLT for surfaces, with higher density materials.
Okay, thank you very much, Agostino.